In lesson 3, we're going to talk about solving systems using elimination. So this is the second method that we can solve a system algebraically. So whenever we solve a system using elimination, the key word here is elimination. So we're trying to eliminate one of the variables so that we can solve for another variable. So what we're going to do is I'm going to kind of run through these steps as I do an example. We always have to decide which variable we're going to eliminate. Sometimes it won't matter. Sometimes there's an easier one. It really, like in the end, it doesn't matter which variable you choose. It's just sometimes one will be easier to eliminate than the other. Sometimes they'll both be, the same difficulty to eliminate, so it won't really matter. So when you look at this first example, I have my two equations, and I want to kind of scan through it first and see, is there a variable that would be easy to eliminate? Meaning, I need to be able to add these two equations together and have one of the variables cancel. So when you look through this, if you notice right here with the y's, if you add y plus negative y, they're going to cancel each other out. So in this case, that's the variable that's going to eliminate. So if you look, if I add these two equations, I'm going to have 2x. The y's cancel because I had a positive and a negative y, and I'll have 6 at the end. So by adding those two equations, I've just eliminated y, and it'll allow me to solve for x. And then once we know x, it's really just like what we did in the last lesson, where we just take that x and we plug it into one of the equations to figure out y. So it's just the first step that's different. When you have substitution, the first step is substituting one equation into the other, solving for one variable, take that variable, plug it into one of the equations to get the second variable. Elimination, the first step is to eliminate, and then you solve for x or y, and then plug in that number to get the second variable. So here I'm just going to finish solving, and I'll be able to get x. So I get x equals 3. So again, you plug this into either equation, just like what we did in substitution. So this can get plugged into either equation. So plug into either equation. I'm not sure why those line segments are showing up, so just kind of ignore those. I don't know why that's happening. So I'm going to plug this into either equation. Whatever one you think is easier to plug into is what you're going to want to do. So it doesn't, in this case, it's not going to really make a huge difference. I'll just pick the first one. So I have x plus y equals 4 is the first equation. So I'm going to go ahead and plug my 3 in. And then subtract 3 from both sides. So we get y equals 1. So again, just like the other examples, you don't want to leave it as what x equals and what y equals. You want to write it as an ordered pair. So my solution is going to be 3, 3, 1. And just make sure that you're putting x in the x position, which is the first coordinate, and then y in the second. So that's it for elimination. Now, there's going to be times, though, the process is the same, but that initial step isn't going to be as easy as, well, one of the variables just cancel. So those steps up there were describing, well, what else could you do if you want to eliminate a variable, but it's not set up to do that. So step 2 here is use the multiplication property of equality on each equation separately. Meaning what we're going to do is we're going to rewrite our equations so that we force a variable to eliminate. If you look at this example, if I added 2x and x, I'm going to get 3x. If I add a negative y plus 3y, I'm just going to have 2y. So I'm not going to be eliminating any variables if I leave this system as is. So what I need to do is I need to choose whatever variable I want, and I'm going to eliminate it. So what we need is we need the number on top and the number on the bottom to be opposites of each other. So one will be, let's say, positive 2, and then this one would have to be negative 2, so that when I add them, they eliminate. Same with the y's. I would need a negative 3 up top and a positive 3 on the bottom, so that when I add them, I get 0. So that's what you're doing. You're choosing whatever variable you want to eliminate, and then you have to create a system so that when you add it, you have a positive and a negative of the same number so that it becomes 0. So let's say I choose to eliminate y here. The only reason why I'm saying y is because I already have a negative and I have a positive. So the only thing that I need to change is I need that top equation to be 3, negative 3y, so that when I add them, I get 0. So because of the properties of equality, whatever you do to one side of the equation, as long as you do it to the other, it's still going to be an equation. I'm going to be able to take this first equation and multiply everything by 3. And the reason why I'm choosing 3 is because I want this value right here to be negative 3y. So in order to create negative 3y, I have to multiply that by a 3. So you're going to multiply every single thing, though, by 3, because you have to remember an equation, whatever you do to one side, you have to do to the other. So what I'm going to do is I'm going to rewrite this. I'm going to distribute that 3. So I'm going to have 6x. Let me just rewrite that. So 6x when I multiply. So I have 6x minus 3y equals 18. And then this bottom equation, I don't need to change because I already have a 3y down there. And there's going to be times where we're going to have to change both, which we'll see in a minute. But for this one, I'm good with just leaving it as is. And then I'm going to go ahead and I'm going to add these two equations. So I have 7x. These are going to cancel, which is what we wanted. And then over here, I'm going to have 21. So divide everything by 7. We get x equals 3. And now you can plug this into either equation. I'm going to say the second equation will be easier just because there's not a number in front of x, but really it doesn't matter because I'm going to have to divide by 3 anyways. So it's whatever you want. I'm just going to use the second equation. So I'm going to use this equation here. And I'm going to take this and I'm going to plug it in for x. So I have 3 plus 3y equals 3. So go ahead and subtract the 3. So I have 3y equals 0. Divide everything by 3. So I get y equals 0. So now I have my solution is going to be 3, 0. And keep in mind, it doesn't matter that I eliminated the y variable. I could have eliminated x and I would have ended up with the same solution. The only difference is I would have gotten y equals 0 first and then had to plug that in to get x equals 3. So either way, you're going to get the same answer. Also, you could check your solution by plugging it into both equations. So, that's something that you don't have to show, but you should definitely always do it just to make sure that you are getting the right answer. So let's look at a couple more examples. So example 3. Now when you scan this equation, you're going to see that, okay, well, I have a 2x and a 3x. Those aren't going to just cancel by adding. 3y and 5y aren't going to just cancel by adding. So you need to change these equations. And when we did the last example, it was convenient because in order to change those equations, one equation was already set up where the bigger number was 3 and the smaller number was -1. And I can easily take -1, multiply it by a number to get 3. But when you compare that to example 3 here, I can't take 2 and make it become -3. I can't take 3 and make it become -5 to add them. So what we have to do is we have to first decide, well, what variable do we want to eliminate? So let's eliminate x's this time just because we haven't done it. And when I look at these, I have to figure out what's the common multiple between 2 and 3. So the LCM between 2 and 3 is going to be 6. 6 is the smallest number that I could use 2 and 3 to multiply to. So what I need to do is I need to create a 6 on top and a -6 on the bottom, or vice versa, a -6 on top and a +6 on the bottom. You need the top and the bottom to be 6 somehow, but one has to be one has to be negative, one has to be positive, so that when you add them, they cancel. So what I'm going to do is I'm going to make a +6 on top. So that means in order to get a +6 right here, I would have to multiply by 3. And I have to multiply everything by 3. So it's going to be 6x minus I forget if that was a plus or a minus. It's a plus. So plus negative or plus 9y equals negative 3. And then at the bottom, you need this 3 to become a negative 6x so that it cancels with positive 6x on top, which means I need to multiply by negative 2 in order to create that to be a negative 6. So you're going to go ahead and distribute the negative. So I have negative 2 times 3 is going to give me negative 6 minus 10y equals 4. Make sure you're paying attention to the negative signs when you're doing this. So now what I'm going to do is I'm going to go ahead and I'm going to add my two equations, and one of the variables should cancel if I've done it correctly. So 6x minus 6x is gone. And then I have negative y equals 1. So divide everything by negative 1 to get y by itself. So we get y equals negative 1. And then you can go ahead and you can plug this into either equation. So let's say I plug it into the first equation. Doesn't matter. So I have 2x plus 3y. So 2x plus 3y equals negative 1. So I'm taking that and I'm plugging it in. So 2x plus 3 times negative 1. Don't forget about that negative. So 2x minus 3 equals negative 1. Add the 3 to both sides. So I have 2x equals 2. Divide everything by 2. We get x equals 1. So notice here I solved for y first and then I found x. So my solution, make sure that you're writing it as an x comma y. So my x is going to be the 1. And my y is negative 1. So comma negative 1. Make sure you're doing x comma y, even though we solved for y first. And again, check your solution, make sure it actually works. Let's just look at a couple more. So this system has fractions. We don't like dealing with fractions. So the first thing I want to do before we even start eliminating this is let's get rid of these fractions. Let's not try to do elimination on fractions. So what I'm going to do is I'm going to take each equation, I'm going to multiply by the LCM. So when you look at this first equation, your denominators, you have 2 and 3 in the denominators. So the smallest common multiple between those is going to be 6. So I'm going to multiply everything by 6 first. So it's going to be 6 times each piece. So 6 times 1/2 is really like thinking of it as 6 divided by 2, so 3x. Then I have 6 times negative 1/3, so negative 2y. And then 6 times 2 gives me 12. So there's the first one. I'm going to do the same thing with the second one. So the second equation, look at the denominators. We have 3 and 4, so that means 12 is going to be my least common multiple. So I'm going to multiply each piece by 12. So here I'm going to have a 3x. Then I'm going to have my 3 and my 12. When I divide 12 by 3, I get 4. So it's going to be 4 times 2 gives me 8. So plus 8y. And then equals 72. 12 times 6. So remember, I got that by dividing. So now I have my new system. So this is going to be my new system. So now I'm going to look at the whole process of let's try to find a variable that's going to eliminate. So when you look at this, look for something that'll be easy to eliminate. I'm looking at right here. I have two 3x's. If I can get one of those to be a negative 3x, then that'll just eliminate them. So let's multiply everything on the top by negative 1. And then what that'll do is that'll make my 3x's cancel. So I'm going to multiply everything on top by negative 1, which essentially just means switch all the signs. So I'm going to have negative 3x. Because remember, it doesn't matter which one's negative, which if it's the top or the bottom equation. So I'm just going to choose the top, and I'm switching all the signs. And then for the bottom equation, I'm just rewriting it. So those are going to cancel. I have 10y. This is going to give me 60. Divide everything by 10. We get y equals 6. So now the last thing you have to do is substitute back in to find x. So let's substitute into, let's use one of our simplified equations. Let's use that 3x minus 2y equals 12. Since that really is equivalent to the 1/2 x minus 1/3 equals 2, let's just use this one instead so that we don't have to deal with the fractions, since we know that they're all equivalent. So I'm going to go ahead and I'm going to plug that in. So really, you can use any of the equations that you've simplified. So I get 12, add the 12 to both sides, we get 24, divide everything by 3, we get x equals 8. Again, you solved for x second, but don't let that change your solution. Your solution is going to be still x comma y. So it's going to be 8 comma 6. Make sure you leave those in parentheses as a ordered pair. So 8 comma 6. All right, just a couple more. So example 5, let's take a look at this. So I look at both sets of variables. It's not going to really matter which one I choose to eliminate. So let's say I choose to eliminate x's here. So that means I have 2 and 4. Always look at the bigger number. 4 is the bigger number here. Can I take that smaller number and get it so that it becomes 4x? And the answer is yes, you can, by multiplying it by a negative 2. So if I multiply 2 by negative 2, it'll become negative 4, which will allow me to cancel that. So I'm going to go ahead and multiply everything by negative 2. So my new equation will be negative 4x minus y times negative 2 is going to be plus 2y. And then it'll be equals negative 4. Down below, I'll just keep it as is. So I have 4x minus 2y equals 12. So go ahead and add these. Those cancel. These cancel. So I have 0 on the left equals 8. So this is one of those unusual cases. We just got something where my variables canceled and I got something that's untrue. So since this is never true, it's just like the substitution examples, where if you get something that's never true, that means there could never be a solution. So there's no solution. These lines, if you were to graph them, would never cross. So they would be parallel. Again, compare the slopes. If I just multiplied everything by negative 2, and I got negative 4x and 4x, and then the y's have the same number, if you were to get these both into y equals mx plus b form, they would have different y-intercepts, and they'd have the same slope, so they would be parallel. So let's look at one other unusual case. So let's look at this one here. What I'm going to do is I'm going to start it off by looking at what's going to cancel. So let's just say I want to cancel the y's this time, just for something different. We haven't done the y's in a while. In order to cancel these, check the smaller number. 3 does go into 6. So now I just need to make one a negative 6 and one a positive 6. On the bottom I have negative 6, so we want to make that negative 3. We need to multiply that by something to get positive 6. Because in the bottom, and we already have negative 6, we want to be able to cancel them. So I'd have to multiply this by a negative 2 in order to get 6 on top. So I'm going to multiply everything by negative 2. So I have negative 8x plus 6y equals negative 4. The bottom I can just keep as is. So go ahead and add them. you're going to see that all of those are canceling, as well as the -4 plus 4 is giving me 0. So I end up getting 0 equals 0 when I do this, which in this case, this is always true. This is always going to work out. So what that really means is that you have infinite solutions. This system is always going to be true for any x and y value that you plug in. So that means we have infinite solutions. And remember what that means graphically is that really you have the same line. So any solution to one equation is going to always be a solution to the other equation, which is why it's always true for any x and y value that satisfies one of the equations. So we have infinite solutions. So you can see that those three scenarios we talked about in lesson 1 still apply to all of the other ways of solving. So you can see what happens when you solve algebraically versus when you have graphically.